Good morning. My name is Captain Larry Smith, the Louisville Fire Department. I'm signed down here at the Louisville Fire Training Academy. This morning we'll be going over the ISTA Manual, Chapter 5 on Principles of Water. So we know water comes in three forms: solid, liquid, and gas. At 32 degrees Fahrenheit, the water will freeze. Anywhere between 32 degrees and 212 degrees, water is at a liquid. And at 212 degrees Fahrenheit, water changes to a gas. What do we know about water? Why do we use water on fires? We know water per gallon is weighed at 8.3 pounds. We know we use water as a cooling mechanism and a smothering mechanism. What are ways that water can be extinguished by fire? We just went over that in the previous slide. Cooling and smothering. Advantages of water. All right, we know water is generally inexpensive and we have lots of it. That's why we might use water. It's greater heat absorbing capacity than many other common agents. Excuse me. We know that steam dissipate heat in well-ventilated rooms due to an increase in volume. So why do we use water? Probably the most important thing is right here. It's generally inexpensive and readily available. So what are the disadvantages when we use water? We know that water is reactive with certain substances, i.e. magnesium. We know it may create operational problems or safety hazard in cold weather. So in the winter times, we know our water can freeze. You flow in a lot of water, so you got ice in front of your structures, you got ice in the streets, ice around your apparatus, ice on your ladders and your elevated master streams. So we know that can be a disadvantage when water freezes. And we know the water is heavy, so water can put a lot of stress on your buildings the longer the incident go, making those structures not as stable as in when we first got there. So advantages and disadvantages we just covered. Facts about water: pressure and velocity. Now, pressure and force are similar, but just slightly different. Okay, pressure is a force per unit area exerted by the liquid or gas. It is measured in pound per square inch, or PSI, and force is a simple measure of weight, directly related to force or gravity. So what we know here is pressure upon the fluid plus the size of an orifice that it flows through is going to determine the speed that water comes out of that hose or of that pipe. Principles. These are found in your book. There are 4 principles, okay? Look over that. I'm not going to go over that right now, but it will be fair game for the test. These are principles. Basically, it tells you that whatever container or whatever the surface is, that the water is going to take on that dimension. 6 principles, I'm sorry, not 4, 6 principles. All right, atmospheric pressure. We know that the atmospheric pressure here on Earth is 14.7 at sea level. Anything below that, vacuum and any pressure less than anything below your atmospheric pressure is going to cause a vacuum, okay? It is greatest at low altitude and it is least at high altitudes. So atmospheric pressure surrounds the earth and exerts pressure on everything, absolutely everything. We talk about head pressure. So in this illustration, we have our water supply up here, okay? It's 100 feet above our hydrant, okay? So we asked ourselves, how do we get to this hydrant pressure of 43.4 psi? Well, for every 1 foot of elevation, you're going to multiply that by 0.434, okay, and that will give you your hydrant pressure. So 100 foot times 0.434 is going to give you what you're going to get out of this hydrant if your water supply is 100 foot above your hydrant. Static pressure is a stored potential energy available to force water through pipes, fitting, hose, and adapter. Water supply not moving is what we call static pressure. Once water begins to flow, once you turn on a hydrant, turn on your faucet, once water begins to flow, it's no longer static pressure and it has to overcome friction. Residual pressure is the amount of pressure not used to overcome friction, loss, or gravity. So you have a water source, and as water moves through the pipes, the fitting, and the hoses or adapter, you got to subtract the pressure from the friction loss or gravity, and that after you do all of that, you will come to your residual pressure. Identify the residual pressure at the location where the reading is taken and not at the flow hydrant. Okay, so you won't, if you're trying to look for a residual pressure, you're not going to get that like at the discharge of the hydrant. You will get that at the end of the nozzle once it flows through your hoses. When water is flowing from a discharge opening, the forward velocity pressure is considered flow pressure. Okay, you will measure that with a pitot gauge, and it is used to calculate the quantity of water flowing, and the size of discharge is unknown. When measuring, when measuring the forward velocity of flow pressure using a nozzle, a smooth bore nozzle must be used with a pitot gauge. Okay, in this slide, we're talking about elevation and altitude. The higher the elevation, or the higher the nozzle is going to be, then you're going to lose your pressure. And if your nozzle is below the pump, you're going to gain pressure. Okay, and then in altitude, the higher the altitude, okay, the higher you are up, the harder it is going to produce an effective stream, versus the lower you are in altitude, it'll be more easy to produce a good stream. Certain amount of pressure is lost due to friction as water moves through pipes, fitting, fire hoses, and adapter. So anytime water have to overcome anything, a pipe, length of a hose, fitting, couplings, nozzle, okay, then pressure is going to be lost. Different types of pressure, and talking about the principle of friction that is found in your book, there are, 4 principles of friction. I'm not going to go into great detail about those. Those are found in your book, so please read them. I'll just read maybe the first and the fourth. The first principle: if all other conditions are the same, friction loss varies directly with the length of a hose or a pipe. So if we have 2 pumpers into a hydrant, you're getting the same amount of hydrant pressure, goes through the pumps, out through the discharge at 200 feet of 1 3/4, everything remaining the same, you're going to get the same amount of pressure. If anything changes, that pressure will be different for each of them. Fourth principle: for a given velocity, friction loss is approximately the same regardless of the pressure of the water. Identify how friction loss principles can be applied to the fire service. So the volume water supplied into a fire hose under pressure is going to equal the volume water expelled from the nozzle. That's pretty self-explanatory. We get water in, okay, we get water out. It's going to be the same volume. Hose diameter determines velocity for a given volume of water. Hose diameter. So the bigger the hose, the more water we'll get. That's basically what that slide is saying. We need to be aware how friction loss and water pressure are affected by the hose length and nozzle use. Friction loss increases as the length of the hose lengthens, okay? So longer the hose, longer that water has to overcome friction loss. Flow pressure always is greater at the source of the supply than at the lowest or the farthest point of the system. So if I got, let's say if my pumper's here, 100 feet of hose, okay, then I turn on the nozzle, my flow pressure is going to be greater than if I had 500 feet of hose and I turn on the nozzle and I take my pressure there. A nozzle is needed to shape the stream of firefighting. We know that. And decreasing the amount of water flow reduces the speed of water and friction loss. There are practical limits to the velocity at which a stream can travel. What this slide is saying, water can only move so fast in a certain orifice. If it overcomes that, then the degree of turbulence can be known as critical velocity. What will happen then is you will either need to use a Siamese or use two different hoses to overcome the friction that will be going through that system. Friction loss in a system can be reduced in several ways. We talked about this. Hose length. We can reduce the length of the hose. Oh, excuse me. Too fast for myself. You can reduce the length of the hose or you can increase the diameter of the hose. So the bigger the hose, the less amount of friction you're gonna have. That's there. Or sharp bends or kink, okay? So we know that sometimes hose get kinked in the yard, in the door, or whatever. So always look down, especially if you're coming in behind the hose man or the nozzle man. Look down, unkink hose if you see a kink, because it's going to affect the amount of water he's getting at the end of the hose. There are multiple factors that can cause a water hammer. All right, so when we're talking about water hammer, we're talking about opening or shutting any kind of gate or discharge, and we know that that can be found here at the nozzle, it can be found here at the discharge, or it can be found here at the hydrant. So this picture illustrates different ways where water hammer can occur, okay? We want to try to reduce that as much as possible. Identify the principles of municipal water supply system. All right, we know that in this city, at least, we have the Ohio River, and so that is going to be our main water supply. For the fire department and local water department, get together, some engineers get together, and they plan where the mains are going to be in the city, where hydrants should be placed, how far apart they should be placed. In your first and second district, they're more closely together. Once you get out in the fourth district, those hydrants are a little bit farther apart, but that is above our pay grade. We really don't determine that, but just be aware of that. Municipal water system may be supplied by groundwater or surface water or a combination of both. So when we're talking about surface waters, we're talking about rivers or lakes, okay? Rivers being the Ohio for us. When we're talking about groundwater, we'll be talking about cisterns, water wells, or water producing springs. So now the question becomes, how do we get the water from the river to our hydrants, okay? There are three methods of moving water in a system. We have direct pumping, we have the gravity system, or we can have a combination system. In the picture to illustrate gravity system, you have the source, you have the source, which would be the river here, comes into the filtration, goes into the pumping system, and out through the city. This here, talk about the gravity system, where your water is above all of this here. It comes down It's fed by gravity. It comes down into your filtration or treatment center and then out through your distribution center. Here you have overhead storage tank, okay? Have water not as high as there, but a combination system where water comes down slightly, goes into your filtration system, and then out through your distribution system. Water may be stored in an elevated reservoir to ensure that water supply when the system is inoperative. So, elevated, in this last picture, you see the elevated storage. So these are found maybe in your chemical plants or in some of your bigger companies where it may come a point where our water system can become effective and not operable. You will have these, and these water can be used for firefighting. It can be used for production of whatever they're making at that particular plant or company, or it can be used for, excuse me, toilets and things like that. Water is treated to remove contaminants that may be detrimental to people's health. Water is treated, to remove contaminants. So you got coagulation, sedimentation, filtration, and all of these are treated through your water treatment plants. Fire department must be aware of situation with water treatment plants that could affect water supply. We got to plan for a potential shortfall. With the river here, I don't think we have to plan for that much, but we also have to plan for maintenance failure, natural disasters, power loss, and of course, if there's a fire. The distribution system receives the water from the pumping station and delivers through the area that it serves. Ability to deliver adequate quantity relies on the capacity of a network of pipes or mains or grid systems, okay? Water mains provides a means for controlling the flow of water through distribution piping. They provide hydrants. They rarely, never have a valve in them. They should be operated at least once a year and should be located frequent intervals throughout a grid system. So Louisville Water Department throughout this city has large grid systems. You should get to know some of those in your district and in your area. They're electronically monitored. So if we have a main break on Eastern Parkway, which we've had a couple of years ago, or even down on Main Street or in the 2nd District, I think we had one over by Shelby and Oak. When we have things like that happen and there's an increase or decrease in pressure, I'm sure there's some alarm that goes off or light that goes off in their control center, and they should be able to then use their computer system to pump water from other grids to make sure areas are getting service, or to shut off water in areas where that break is, so it's not feeding and causing more damage than the break itself. Water departments must have the ability to promptly operate valves during emergency or equipment breakdown. Just went over that. Valves for water system are broadly divided into two main types. You have indicating valve. The two types we should be familiar with is the post-indicator valve and the OS and Y valve. And then you have non-indicating valves, and most of these are underground, may be found in boxes or manholes. All right. Control valves in public water distribution system are generally, gate valves. Rising stem valves, these are similar to our OS and Y valves, and non-rising stem valves. Proper valve installation and maintenance can affect fire department operation. It's necessary to close off 1 or 2 hydrants while a single break is being repaired. This is on properly installing valves, and less advantages if all valves are not maintained and kept fully open. High friction loss caused by partially open valves. Closed valves may not be noticeable during ordinary domestic water use. It is difficult obtaining water for firefighting. So if someone in the city is working on a valve and they finish and they do not open it back up completely, you may not notice that if you live in that neighborhood and you're taking a shower, brushing your teeth, watering your grass. But if your house catch on fire and we need to open a hydrant or several hydrants in that area, it will be noticed with the reduced pressure of what a hydrant is giving us. That's when you would notice something like that. Okay? Underground water pipes may be made of many materials and is suited for a variety of conditions and pressures. Especially in our city, we have a lot of old mains and pipes running through the city. They can be made of cast iron, asbestos, cement, steel, plastic, concrete. They don't replace these much until there is a problem because they're so old and it takes a lot of work to do. So that's why they're not replaced. But anytime they do replace them, they replace them with better, lighter weight material that will can be easily fixed. And that's what this part of the slide says. They are reinforced when it's unstable or corrosive soil is difficult to access the area. Underground water pipes may be made of many materials and suited for a variety of conditions and pressure. Internal surface offers resistance to water flow and factors affecting water flow and friction loss, which is incrustation of minerals, sedimentation, and it reduces by flushing hydrants periodically. So these are things that underground water pipes may be made of many materials suited for a variety of conditions and pressure. Flushing hydrants, we don't do that. I think out in the county, they're responsible for doing that in their fire district. Okay, rates of consumption can be used to determine the adequacy of water in a distribution system. Okay, when we talk about rate of consumptions, we're talking about the average daily consumption, the maximum daily consumption, and the peak hourly consumption. The average daily consumption is the amount of water used per day over a period of 1 year. The maximum daily consumption would be the maximum amount of water during any 24-hour interval during the peak during the time of 3 years. So over any 24-hour interval during 3 years. And then your peak hour consumption would be the max amount of water used in any 1 hour interval over the course of a day. So when we're talking about the peak hourly consumption, it's normally going to be higher in the morning, maybe between 7 and 10 a.m. when people are waking up, brushing their teeth, taking showers, getting ready for work. And in the evenings, maybe between 8 and 11, people are doing the same thing, taking showers, brushing their teeth, getting ready for bed. That's when your peak hour of consumption will take place. Various ways of moving water through a system we talked about. Describe private water supply system. We know the purposes are some purposes is strictly for fire protection. It can be used for sanitary and fire protection and manufacturing. We, as a department, would not use a private hydrant unless last resort, pretty much. We don't know if they're serviced. Most of the times they're not serviced by the city, so we don't take a chance of using private hydrant. Sometimes these private systems are used in manufacturing whatever is going on their property, or it can be used also for sanitary and or fire protection. Private and municipal systems may work independently or together to distribute water to an area. They're designed similar to municipal systems. They may be supplied from municipal or own water supply source, and usually maintain separate piping for fire protection and domestic and industrial services. Fire departments should make arrangements to augment private water supplies if necessary. So if all else fails, we can draw from a reliable static water source close to the scene. Close to the scene. So we need to know where our swimming pools are, where large cisterns may be. If things get really bad, we need to know if we have enough hard section hose to drive from the river. Things got to be really, really bad. What are the purposes of a private water supply system? We went over that in a previous slide. So in summary, pumping apparatus driver operators must understand the properties of water and how it functions as an efficient and economical extinguishing agent. We know we have plenty of water in this city because we have a river. The principles of pressure and friction loss are factors that must be considered during every water supply operation in order to properly supply pumpers and attack hose. So we know anytime water goes through a hose, an orifice, a pipe, that it's going to and have to overcome friction. Pre-incident knowledge of the water distribution system serving a local jurisdiction and an understanding of the design and proper maintenance of a municipal or private water system is vital to providing needed water flow and will aid driver operators in planning for large-scale firefighting operations. So we need to know, or at least have a working knowledge of where our water is coming from, our grid system, where our hydrants are. That's why we do street and water exams, knowing where our first hydrant is, where our second hydrant is, having a working knowledge of our first alarm district, where our water is. In the first, second district, even the third district, our hydrants are pretty readily and pretty close together. As you get out into our fourth district, our hydrants are more further apart. So having a working knowledge of that will aid you and help you in case you have a fire incident. So that's chapter 5 of water supply systems.